Probando, probando. Probando, probando. Ok. Hello everyone. Welcome back. My name is Ishmael and I will be repeating the stream because I didn't have my microphone properly connected. So just give me a moment to share this for anyone that is interested. Okay, let's see here. Mic was wrong. Take two. LOL. Okay, let me copy this. Select, copy, send. Now let's do it here as well. Take two. Then let me do this on Mastodon. Oh, okay, let's send this. Take two. And finally, well, I think that's it. I hope let me see. Okay, I'll give just a moment for people to assemble. Let me test. Okay, yeah, I have audio. Okay, I will cut this off the final video. I hope our viewer can come back. Okay, anyway, let's start over. So let me go back all the way. Okay, so again, let me put the timer, create new one, and this will be 1 hour again. I don't like this color. Okay. What? I said 12. I don't understand this. Okay, let's just do done. Okay. Has expired. Okay, K alarm. I don't know what you mean by this. Let's just use the normal clock. Temperature 1 hour. Excellent. Okay. So, hello everyone. My name is Ishmael. Thank you for watching the stream. I had to repeat this stream because I had some problem with the audio. But okay, let's give it a shot again. So today we are going to continue where we left behind the last time. Last time we finished reviewing this, but today we are going to continue with the documentation and the commentary, okay? At the end I will show you more links that will be useful if you want to explore those. So let's just give it a quick recap here. If you click restart here, well, let me start fresh actually. So let me just reload this page. And if we click here run, we will see hello world. We can also step here, pushing the address of the first letter of this string, which is 0112. Then we push the byte for the letter H, capital H, duplicate it here. Then we test, is this non-zero? If it is non-zero, we will jump here. And then after this anonymous label, we continue with this code, which will push the device port for the console device, console write, and then we output the first letter. Okay, and we do this with everyone until we reach this 0 byte, at which point this test will fail. We will not jump here, but we instead continue here. Okay, so let's continue this. It says, let me just double this, okay. I am going to create two windows. Okay, and here it says, a word starting with @ defines a label, and one starting with semicolon pushes the absolute address of a label to the stack. The absolute address is always 2 bytes. Okay. Then the first instruction here is to push the absolute address of a text label. Okay. So semicolon text pushes the 2 bytes equal to the address of the @text label to the stack. In the interpreter above, press step to walk through each step of the evaluation. Okay, we have already done that. Next, we define a new label named @while to mark the start of the loop that will print each character to stored at the text label. Okay. So remember, this is a label and this is a label as well. Then the load absolute keep opcode loads a byte at the address currently at the top of the stack. In this case, the ASCII letter H, capital H, which is the byte 48. The K mode indicates that the operator will not consume the address. Okay. So let's give here a quick look. So the null byte is 00. Let's see. We also use regularly a space. A space is this byte 20. 09 is the tab. Where it is horizontal tab 09. And the line feed is 0A. Okay, after that it comes to, after 20 hexadecimal, it starts the actual characters, the printable characters. Everything before the space is called a non-printable ASCII. Okay, and everything that follows is the ASCII table we all know. First come the capital letters, then the lowercase letters, some symbols, and after 7F is the extended ASCII table. We will not use this a lot, but it is good to know this one exists up to FF. Okay. Now let me just test that my microphone is still working. Yes, it is still working. Okay. The dup opcode makes a copy of the letter, so we can test this because this test will consume the letter, and pops that letter from the stack, and if it's not 0, we jump to the corresponding closing bracket, which is an anonymous label. Okay, so what does this mean? So for example, I could put here a new label. Let's say this is called skip, and here I said add skip. If I restart this, you will see that it's still working. Okay, so these curly braces are just a way to make anonymous label. This one at the end is the anonymous label, and this open brace is just telling us to jump to the matching closing brace, because we can nest this. We could have something like this, as long as it is properly nested. So this would be evaluated first, and if we fall through, then this one would be evaluated next. Okay, in this case we don't need that, but it's useful to know how you can use them. Okay, then I also wanted to show you here there is also a website for showcasing hexadecimal numbers. So you can represent it like this. It teaches you how to count with your fingers, how to do verbal counting as well, an hexadecimal to binary table, and lots of other stuff that are not particularly related to Occidental at this moment. But feel free to explore this on your own. And if you have any kind of question, just let me know. Okay, so now this is the disassembly of this code that we have here. So remember that all the code starts running at this address. So this is implicit here. We could add it like this. And this is very important as well. Normally you have to use the 4 digits of hexadecimal to represent a short. So when we have only 1 byte, it's called a byte. When we have 2 bytes that we want to interpret as a bigger number, this type of number is called a short. Okay. The only time where we can use less than either, for example, here 2 digits is when we use the padding runes. Okay. And we have seen this before. For example, if I do 18 at console write, and then I told you that this was representing that this port is only 1 byte. Okay, so if you see here, I don't have to put 01 or 0001. This is just for convenience, but this will only work with relative pad rune and absolute pad rune. So here I also can just put 18 instead of 0018. And the same, I can just put here 100 for convenience, but you can put it anyway. And if you want to put this 0 here, it is fine. Okay. Remember that this 18 is the one that we are pushing here, so we could replace this with dot console write, and it will also push this value 18. Okay. But remember also, after using this syntax, we need to put this again. And in this case, it is not implicit. Okay, so if I miss this line here, since we have changed the absolute padding, if I try to restart this, it will tell me that we are writing in 0 page. So I need to put yes or yes this absolute path to 256 decimal. Okay. Again, if I remove all usage of absolute padding, then it is implicit that we are starting at that address, like this. Let's say also, let's say we want to, just for the sake of this, okay, no, actually let's do this. Let's push 0, 1. If we restart, you will see that it actually pushed 0, 1 as we expected. But remember that using less than 2 or 4 digits is only possible with absolute or relative padding. So for example, if I just put a hashtag 1, it is an error. Okay, this is an invalid number. Okay, so even though we don't see this here, remember that this is implicit as long as we don't use any more absolute runes. But we can put it. I always use this anyways. So we are starting at this address, A0, restart. A0 is lit 2. Lit 2 is going to push the short representing the absolute address of the capital H, which in this case is 0112. After this, we have the load absolute keep instruction, which in hexadecimal is 94, and so on until we get here to the GCI. GCI. Here, GCI stands for jump conditional immediate, and it's telling us to jump 3 bytes ahead. So 1, 2, 3 bytes is where this label, anonymous label, is. And remember, if this is non-zero, it will jump these 3 bytes up to here. Okay, then we have here the pop 2, and the break. Break is the null byte. So again, this, for example, means that I could change this 0, 0 to break, and this break to 0, 0, and it will be exactly the same. Okay, and I can also, for example, replace load absolute keep with the raw hexadecimal 94, and it will still work the same. Now this disassembly is actually valid code. So let's try loading it like this. We need all the snippets that we have here, and we need the text. Okay, so if I finish, let's see, there is some kind of error here. Inc2. Okay, there is the first H. We increment, so we are here in Inc2, and then we're going to jump to the while up here. Okay, and then we have 6, 5. Okay, I don't know why it's not using here the space, because I see that we have it here. But I will just remember to check this so we can send a pull request to the documentation in case it is actually wrong and I just didn't do anything mistakenly. So let's say pull request .org, and we want CMAX, which is just Emacs in the terminal. Okay, let's just put check disassembly in hello world. Okay. So let's continue here. But basically what this means is that we could replace all the instructions with just the hexadecimal values, and it would still be, let's build this. Let's store this in code. Oh no, we had a specific UXN here, and let's call this hello. So we save this, cd UXN, and there it is, the hello.ram. Okay. Remember, we can use hex dump, capital C option, to see the actual dump here. And for example, if we just copy paste this here, and then this should still be valid code. Okay, so let's restart, and there we go. So we can always replace the mnemonic of the opcodes for the actual bytes that they represent. So this substitution is done by the assembler. And now also I have Oxen this, yes. So this is the disassembler, and I can show you later how to install it. But this one is basically the one that is giving us this this syntax here. And the cool thing about this disassembler is that the output is actually valid code as well. Okay. So I just need to check later that we don't have any mistakes with this and this. But I don't know why there would be an issue. So now that we have checked that this syntax is valid occidental, and that the hex dump itself as well is valid occidental, this one, well, without this, just the bytes, this is valid code. Okay, so we could also say that occidental is homoiconic, which means that its representation for code and data is the same. Now let's continue here. The 1/8 word pushes a number to the stack, which maps to the console write port, followed by DEO opcode that pops both bytes, the letter and the port, and sends the letter to that device port, telling the console to print it, leaving only the address on the top of the stack. Okay, let's review this. So if we step until we print the first character, okay, we will see that it consumed the, so we have here the absolute address, then we load the byte without consuming the address, and then we duplicate it. We are at this point on the dup. We test, it is non-zero, so we jump here. Then we push the 1/8, which is the which is this port, console write, and after this it will DEO will consume these 2 bytes, print the letter H, okay, and then we continue with Ink2. So it is important that we use the correct modes. Let's see what happens if I miss this K here. It will push the address, then it will load the byte, but will consume the address. So by the time we get to Ink2, it will have nothing to increment, or it will just increment 0. Okay, let's put K here again, and let's see what happens if I miss the short mode in this ink instruction. And let's put this label at 1FFF. Okay, so let's restart. Okay, so now the text data is at 1FFF. We push the byte, we duplicate it, we test it, then we add the device port, and we output the first letter. After that, we are going to perform this ink. But the difference is that Ink2 will treat these 2 bytes as a short, as a bigger number. If we don't use the short mode with the 2, it will just increment this one. But since we are using unsigned bytes, it will just wrap around to 0. So let's see this. We incremented, and now we are at 0, 0. Okay, so this will of course break the rest of the code. We need to put the 2 here for short mode, and it works again. Also, for example, if we mess this DEO and we use DEO 2, the short mode, this also breaks. Let's see why. So we start with 1FFF, then we push the byte here, we duplicate it, we test it, then we push 18, and now we are going to DEO2. But DEO2 is going to push to this address the following 2 bytes, and that will leave our first address incomplete. Okay, so that is why it fails here, and if we finish it, it just doesn't work. So one of the main reasons where you can have errors in UXN is this kind of semantic errors when you don't use the correct opcode. Remember that when we are programming, we usually have syntax errors, runtime errors, and semantic errors. So a syntax error would be something like having an invalid comment. Okay, so we have a comment open. We would need to put this with a space. Okay, that is a syntax error. Runtime errors are when the syntax has already been validated, and while we are running the program, it fails. There is actually something really cool about UXN, in that it, by default, it doesn't error at runtime. Okay, so for example, let's see what happens if we start with an empty. So this obviously is 0 bytes and the stack is clean. What happens if we do a pop? Normally in this kind of environments, be it Forth or any other language that uses stack this way, this would be an error. However, you can see that the bar here disappeared. That is because we actually consumed the last byte. So this means that the stack is circular. Okay, so there are no stack underflows. There are also no stack overflows. And the other kind of error that could be done at runtime would be, for example, 10 divided by 0. This is not an error, it will just give us 0. Okay, so when we divide by 0, we just yield 0. And this way, with these three errors being handled in this way, it is said that it is impossible for the virtual machine to crash due to any of these kind of errors. I don't know if I have a fourth here. Retro. So for example, this is fourth. I think in fourth is drop. Okay, so you can see that with an empty stack, if I drop, this is the equivalent of pop in UXN, it is an error. Okay, so if and it also, it's not just an error, like it crashed, it brought me back to the console, because for this retro interpreter, it wouldn't make sense to continue or try to fix this. It is just like in Python. If, for example, if I do 1 divided by 0, it will tell me it is a 0 division error. Okay, but if, for example, I have this in a file, let's say 0.py, and then I do Python 0.py, it errors, and also this is like an exception, it's called in other languages. Okay, so we can have this in 0.tal, and let's just say 0a00 Also, as you can see here, I am pushing these 2 bytes at once. I could have also done like first push 0a and then push 00 and then do the division. But this is actually 1, 2, 3, 4, 5 bytes. We can merge this, and it will be the byte that pushes the next 2. So we are saving 1 byte here. Okay, let's save this. Then 0.tal, 0.rom, and oh, I actually need to show, so 0e 010e do. Remember that 0e is the debug port. I always remember, because I say like, okay, E is for error. And remember, we can also create the label, which I will do just not to confuse you anymore. So 0e is at system debug. It is 1 byte. And here we just push system debug. Okay. So let's see what this does. Writing in 0 page. Oh yeah, remember when we used this syntax, we always have to put the address here, so we know we are starting the code at this point. And now oxencli 0.rom. We can see that the division is not an error, it just gave us 0, 0. Also, let's see what happens if we do a pop. Okay, so we reassemble and then we run it. And you can see that remember that I told you that this indicates the stack pointer. So it grabbed back to FF, to the maximum value. Okay. It was not a stack underflow like in other systems that use stacks. This is very clever because with this we avoid these kinds of errors at runtime in UXN. Okay, now the into opcode increments the address, moving the text pointer to the next letter. The to mode or short mode is used because this address is made of 2 bytes. Okay, so this is inside after the lambda. Remember, this would be lambda 00, and after this we have push 1 byte, so lit is 80, and then the byte we want to push. DO is 17 and int2 is 21. In this case here, this is telling us to jump back, and this is assigned short. Okay, so for example, if we are here in while, we have to jump back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bytes. Okay, so this would be like negative 15. Then finally with bang while, we jump back to the at while label and repeat the loop until there are no more letters left to load. When that happens, we pop to remove the duplicated letter, and we pop 2 to remove the address on the stack to keep the stack clean at the end of the evaluation. And here we can see how the textual data is represented. So it starts at this address. Let's step. Okay, so remember, the first byte 48 for capital H is at this address. And then the following bytes are just laid out consecutively until we reach 00 here. Now I said that the putting here absolute of 100, which is hexadecimal, which is decimal 256. This is where the program starts, and this is implicit as long as we don't change this using, for example, 0, 1. Let's say this is true. Okay, so this is valid. But remember, if I forget this one here, then it is an error. It thinks we are trying to write just at in 0 page at the address which would be 0002, the next address after this. And for that we need to put this. Okay, so just remember, whenever you see writing at 0 page, that means you forgot to put this. And also, when the memory starts, when the RAM is zeroed before UXN is initialized, so this one is also implicit at the end, and it will run perfectly, because after this byte for the bang or exclamation mark, it is just filled with zeros, the memory. However, for just to make it more clear, we put this null terminator. Okay, because what happens if we have another string? Let's say a string 2 is goodbye world. Okay, so if we restart this, we can see that it only printed hello world. But if we miss this null terminator, it will actually continue until it finds the one that is at the end of the RAM, okay, of the used RAM. So just remember, all your strings needs to be null terminated, or they must be counted strings, but that is for another lesson. the previous session I introduced you to macros. So what I typically do is that I just create macros for the space, a macro for the new line, which is 0a for 10, a macro for the null byte, like this. Okay, so at least to me this is more readable. So I would just put this is a space, and actually let's put a new line here and restart, and there we go. Remember we missed this one, so let's put the space here. So even though this is one label and this is another label, if we don't put the null terminator here, it will just continue to whatever is after this. And after this, there could be also some code. So for example, let's just copy this code. And let's say, okay, so we have some code here. It is not very readable, right? So let's just remove these comments. But just imagine we have some sort of routine here, okay? So this is do something. Oh, we are not saving, we are not in a file. And if we don't put the null byte, it will just continue happily printing the code that is following this. So you can see that in this case it just printed two like non-printable characters or some bytes that it doesn't know of, because it stopped here in this break. Yes, because this is not being interpreted, this is just being read as... Oh, actually it would have stopped here in the 003, because remember here this is 20,003. So when it sees this 00, it will interpret that as the null byte and finish. If we, for example, remove this test here and restart, you can see that it actually continues until it reaches the end here, because here is an implicit 00 or an implicit null byte. So just remember to put your null bytes to the limit where your string ends. Let's see here the summary. So in short, comments are within parentheses. Numbers are always lowercase. This is very important. For example, let's say I want to put this label at 2FFF, and you can see that this works. But if I try to use capital F, it doesn't. Okay? So this is useful when, for example, you want to create a label that is only hexadecimal digits, like cafe. Okay, and we need to push here. We change this to cafe, and we run it, and it runs without any issue. But what happens if I try to use lowercase here? Since all of these letters are valid hexadecimals, UXN wouldn't be able to know if you mean this hexadecimal number or this as a label. So it doesn't reject it, and this is another error, at least in this implementation, because I'm pretty sure it's not going to work here. So let's say we want to push the address of cafe, and cafe is here. So we're going to break and then add cafe. Let's see. Okay, this is weird. I think this is another error. So lowercase x labels are valid. Yes, I believe this should be an error. Let's just give it a last test with the old C emulator oxnasm. So C oxnasm hello dot rom hello dot tal. Oh no, we are in 0.tal 0.rom, and here it says invalid at cafe. Okay, so please do not use, even though it's working at this moment, I'm very certain that this is an error and it will be fixed later. Okay, so lowercase hexadecimal shorts or bytes and opcodes are uppercase reserved words. Okay, so this needs to be text, and here it is text. Okay, this is working. But what happens if I try to do this? Load absolute keep in lowercase. Then it says this is an invalid reference. The same as if the modes are always in lowercase. So if I do load absolute keep with capital K, it is also an error. Okay, so just remember that. We haven't seen this yet, but there is also an R mode for return, and this one also needs to be in lowercase. The two, well, of course, there is no other option, so that works. So remember, numbers are in lowercase hexadecimal and opcodes are uppercased. A rune is a non-alphanumeric symbol at the start of a word. Literal numbers are prefixed with the hashtag rune. Addressing is done by one of 6 runes. Labels and macros are unique, non-numeric, non-opcode, and non-runic symbols. So labels and macros are unique, non-numeric. That is why this should fail. But I'm pretty sure that by the next video this will be fixed. So now let's see all the basically this is all the syntax in UXN. It is very simple. So we have the absolute path, which we have seen here. We have the relative path. Let's try this one. So let's do micro example.tal. So we are going to use absolute path with 1.8 for at console write. And remember, this is just the way these are defined here, console write, but you could put something like, for example, in Spanish it would be escribir, and this would be consola escribir. Okay, and it doesn't matter, it is not enforced by the assembler nor anything. You can call your labels whatever you want, you just need to be consistent. Okay, so we start at 1.8 console write, and then we have this relative path of 1 byte. Okay, now let's see what happens when we push console write, and then here let's say that we have another label foo, which comes after console write. Then we push foo, and at the end we are going to 010EDO, which is send a null byte to the system debug port. Okay, let me just save this, quit, split. Okay, so this is the example, and here we say Driflim. Driflim is the assembler. I think we didn't see this in the previous session, but we are going to build it after this example. Okay, so we have example.tal, example.rom, and once we finish this, we are going to use uxuncli example.rom. Okay, and this is what we have. So first we push the value for console write, which is 18, and then we push the value of foo, which is 19. What happens if we leave out this $1? I'm going to save this again, and as you can see, both foo and console write have this same value. I need to use the relative path of 1 byte to tell okay, so now we are not in 18, we are actually in 19, and this is the same as doing this, for example. Okay, if I do it this way, it is going to work 18, 19, but usually we don't do that. For example, this is useful for things like, let's say we want to create some kind of enumeration. So enumerations always start at 0. Okay. Another way we can use these absolute and relative paths is with labels. So for example, I can say I want an enum. So this is the same as 0 as putting this. Okay. We are at address 0. So the enumerator always starts at 0, and then we have suites. Let's say we have, I think it's called clubs, spades, hearts, and the other one is diamonds. Okay, and now let's try pushing some of this. So now we have new syntax here that is also being described in the summary here. The child label. So this is a parent label, which we have been using, and this is a child label. So that means that all these sub-labels are part of this parent label here. Let's try seeing what the values of these are. Let's push suites, and then let's push suites / clubs, and then we are going to see the result here. Okay, let me clean the screen and run this again. You can see that we started with suites being on 0, and then clubs it's also at 0. Why? Because we didn't we are not putting any relative padding here. Okay, so we could say here, okay, so clubs is 1 byte, spades is 1 byte, hearts are 1 byte, and diamonds are 1 byte as well. And in this case, between suites and suites clubs, there is no relative padding, so it's still going to be 0. But now let's try with something different, like spades. We save this, and now we have the first one was 0, and the next one is 1, 0, 1. We can also define, for example, here 0, 1 is a byte, 0, 2 is a short. Okay, and then we could change these ones like this: byte, byte, byte. And what I like to do here is just to order them like this. Okay, so now we have new syntax. These brackets, these are ignored. These are just for organization purpose. Okay, so let's save this, run this again, and there we go. So usually we wouldn't use suites alone like this because we want the members of our enumeration. So suites, spades, hearts, suites, what is the diamonds? Oh, and the first one was suites, clubs. Now if we clean the screen and do this again, we can see we have 0, 0, 1, 0, 2, and 0, 3 as we expected. So that covers absolute and relative padding runes. We also have the literal. So literals are the same as doing, for example, 1, 3, 3, 7. This is the same as saying lit 2, 1, 3, 3, 7. Okay, so this is a raw byte. This is a raw short, and this is a literal short. So when we run this code, we will see that it pushes 1337 twice. Okay, so these two syntaxes are the same. But we could also say that we want 1, 3, and then 3, 7. Okay, if we save this, we can see that is the same. However, now we are using 1 byte more, 11 bytes now, and the previous run was 10 bytes. Because this, remember, this is the same as lit 2, which is 1 byte, and then the following 2 bytes for the actual value. However, here we have lit 1, 3, and then lit 3, 7. Okay, so this is actually 4 bytes. Whenever we want to push 2 bytes as one value, it is better to just use lit 2. Okay, and we can have this space, it doesn't matter. Just don't break it like this or like this. Okay, it can either be 4 digits or 2 digits, it doesn't matter. And there we go. We again pushed this value twice. Now we already seen parent and child labels. We also saw ASCII runes. So when we had the, for example, let's say we want to push the star, and then we want to push 1/8 and DO. Remember, 1/8 is the console write port. If we run this, it will print the star. So this one is the same as saying 2A, I believe that's the value. Or we can just say 2A 1/8 and then DO. And it will print 2 stars now. Okay. So that covers the ASCII rune. And then we have the addressing runes. These are 6 in total. We have seen comments. We have seen the beginning of the anonymous labels. This one is ignored. We have also created some macros, and we have used these two. The only one that is left is seeing what all this one does. So we are almost finishing the 1 hour. So let's try to do this as quick as possible. Okay, now let's see. In this example, let's say we have a label, just called label. And this label, we have at the beginning, we'll start here. We are going to push label. Then we are going to push label with this. Then let's see. Okay. Oh, and we also have, actually let's do it in the 0 page. So let's say that at 4.2 we have this label. Okay. So we are going to push the value of this label here using these two different runes. Then we are going to debug. And this is what happens. So when we use dot, the literal 0 page, we are just pushing this byte for 2. But when we use the semicolon for the literal absolute, we are pushing 0042. So this is the same as using 0042 here. Let's run this again. And as you can see, it is exactly the same. Now let's see here. Whenever you are using this syntax, either be a literal hexadecimal or a raw hexadecimal. So for example, 1337 is a raw hexadecimal, and hashtag 1337 is a literal. So this will be pushed, and this is just some bytes in memory. So for example, whenever we are making these numbers, so when we have them raw, we can separate by 2 digits. As I said previously, we cannot do this because this is illegal or invalid. Again, in this case, this would be pushing just 1 byte, and then the next one is a raw byte. If we want this to be part of the same command, there cannot be any spaces in here. But if we use lit 2, then this is valid. Okay, this is valid like this. Just remember that as well in raw hexadecimals, we cannot separate like this or like this. It needs to be 4 digits or 2 digits together. The only exception for this is when we are using the paths, either the absolute or the relative paths. This is just for convenience. For example, here we could put 0100, but just to make this easier, we'll just say 100. And again, when we use the relative, we have been using this like just 1 instead of 01 or 0001. But remember, this is the only place where you can do this. You cannot do this with the literals. Okay, so this is not legal. And also just 3 digits like this would also be invalid, and more digits would be invalid as well. Okay, so because remember, this is the lowest possible number, and this is the highest possible number that we have available. So now let's see what happens when we push this. and our time is up. Okay, so let's try to wrap this up. Let me just finish this explanation. 0, 1, 0, E, D, O. And let's clean the stack, print again. So this is what we had previously. Now let's just say that after this code, I have another label. So this is label 2. Now let's call label 2, and finally, comma, label 2. Let's reassemble this. And now this label starts at 010C. Okay, let's make this explicit just for this example. And remember, we can remove this 0 because we are using the absolute path here. Let's run this again, and you can see it is exactly the same. So now the 0 page, literal 0 page, is just giving us these 2 bytes. The absolute literal is giving us the whole address, and the literal relative is telling us how many bytes from this instruction is the label. So in this case, it is 4 bytes. So at this point, we have 1, 2, 3, 4. Wouldn't this be 5? And then the label. Okay, so it is 4. So here is 0, 1, 2, 3, 4. This would be 5. Wouldn't it? Okay, so maybe I don't know exactly why it's 4 here. Because again, remember, this is just lit 2. So this is 1 byte, 2 bytes, 3 bytes, 4 bytes, and this break is another byte. So I would expect this to be 5. Let's put another break. No. It says 4. And it shouldn't matter if this is like this. Oh, okay, yes. I get it now. So I just need to remove this. Yes, there we go. Yeah, so the error was because I had the absolute path, and we were pushing more bytes here. So let's remove this, put our break, and run this again. 1, 2, 3, 1, 2, 3, 4, 5. Yeah, I don't get it. Break. Now it should be 5, right? Yes. So it may be that it is actually 4 plus 1 to get to the actual label position. But anyway, I never see these values, or I never calculate them manually. I just let the assembler do this for me. But that's what this one does. And now these other ones, these are raw. So instead of pushing the bytes, this will just leave the bytes, but as raw values. Okay. This will not work if we try to run this, because these raw values will try to be executed as bytecode. Okay, so in this case what we are going to do is just see the effect of this. So if I try to evaluate it and run it, it's not going to do anything sensible, but we can do xdump, and this is example.rom, and we can see here that we have 80 is, this is the same as saying lit 05 for this one. This one other would be lit 2 0105, and this last one would, oh no, I'm sorry, not lit, because this is just raw. The first lit is this dot, so this is the same as 05 like this. These are all equivalent in this case. But what is the raw? This is raw. Oh, okay, it needed to be like this, yes. So let's repeat this. I'm sorry for the confusion. Okay, there we go. So this one is 04, this one is 0104, and this one is just FF. Okay. But basically the only difference is that this will write the byte or the short directly to RAM, and these ones will actually push the value of that either byte or short to the stack. Okay. Now please let me know if this was more confusing, because I got a little bit nervous because the first iteration of this stream failed. My microphone was not working correctly, so I felt like I had to rush up things a little bit, because I have some things that I need to do. But with this table here, we have finished the first part of this reference. If we go back to the top, we can see we have sections for stacks, notation, opcodes, and so on. So if we go just to syntax, we will see that it is what we have seen up until this table. So below that is the next section for stacks, which will be for the next session. And again, I'm sorry for the ones that were present on the stream and it failed. I had no microphone. Please let me know any feedback, because this is my first time doing this, so I really want to improve. I don't want to confuse you. So if you think this explanation was not fulfilling, just please let me know. We can either chat, or I can even make another video just correcting myself if I made a mistake. Whatever you need, I want this to be a useful resource. So next time we will start with UXN stacks, or probably we can, yeah, let's continue with UXN stacks, and then at the end we will okay, so probably next time we can see this example along with this. But I don't want to go too deep into all these examples. Feel free to do this by yourself. For example, this one for debugging should already be understandable if you have followed the previous two, well, this one and the previous recording. But we have not seen functions, variables. So just let's just continue next time on stack and install stacks here as well. I did promise that I was going to teach you how to create the new assembler. Okay, so we are here at UXN. This is all we have up until now, and by the next session I'm going to make sure to upload this to a repository so we can follow along. If you want the latest assemblers, just go to Drifblim. Okay, let's first see what is Drifblim because I didn't know. So Drifblim apparently is a Pokemon. And Drifloon, if you remember, on the first session we used Drifloon first. This is like the standard Pokemon, and Drifblim is like the evolution. Okay, so on the first session we used Drifloon, and now we are going to learn how to use Drifblim. So for this we go to Drifblim and just add UXN, and let's go to everything, and I think we can go from here. It should tell us view source, and this is the repository. So we are going to copy this and clone this. Clone Drifblim. Oh, yes. I need to put git clone. Then we change into Drifblim. And here we just simply run make. Okay, make, and there we have bin drifblim.rom in so many bytes. We can copy this. We can copy bin drifblim. So it created drifblim.rom and just drifblim. Okay, anyway, so you can have drifblim.rom. Here, for example, we are going to copy it to the parent folder. Now we move to the parent folder and we should have here drifblim.rom. What I like to do after this is create a script. So for example, micro drifblim. Oh, we already have a directory called drifblim. So let's call it just whatever you like. Assembler. We have a hash, a shebang for user bin esh, and then we just call oxencli drifblim.rom, and we will pass all the arguments like this. Then we need to change the permissions to add executable to assembler, and then we can actually run our assembler, and it tells us it needs an input and an output. So we can say assembler hello.tal, and the output is hello.rom. There is something wrong with that one. Let's go to example. Example.rom, example.tal. Okay, there we go. So I needed to change the name because we already have here the Drifblim folder. What I actually have in my system, if I go to bin, I have here Drifblim, I have Drifloon. Okay, so if let's see what is in Drifblim. It's just what I told you. Okay, in this case I just have all my ROMs in this directory, but besides that it is the same. I also changed here the extension, but it doesn't matter to UXN if you use ROM or whatever you want, or even if you just leave out the extension. Okay, the other thing I want to do, just in case it is more comfortable for you, is there is another assembler here, but let's read the makefile. So this one is called Drif. Okay, so I'm going to copy this and say make bin drif.rom. Okay, so it has assembled another ROM. We can see here in bin we now have drif.rom. So we have been using up until now UXN CLI, for example bin drif.rom, and what is happening? There is no output. Okay, don't worry, we only need to use the emulator, the UXN EMU, which is the graphical user interface. Hey Bob. So Bob has said hi on the chat. Hi Bob. And this will give us this GUI interface. Here we can say, okay, we are inside this folder. Let's go back to the other one. Let's just copy bin drif.rom to the parent folder, go to the parent folder, and then run the same command with xnemu. Okay, now in this folder with F1 you can make this bigger. Okay, so let's write here example.tal. With tab we can move to the other one, example.rom, and we just click assemble, and there we go, assembled in 4 bytes. Okay, so now that I use this, there is actually an issue with how this is scaling. So for example here it is scaling when I click assemble. Probably it will scale just when I click assemble. Okay, so this is another bug. Let's just report this. So drif.rom zooms in when clicking assemble if zoom level was changed. Yes, save that. Okay, so with this we have the UXN CLI, UXN EMU. We have used both emulators. We have also used the Drifloon assembler, the Drifblim assembler, and the Drif assembler. This is just called Drif. And feel free to use whichever one you like the most. Just please remember that you cannot do things here like for example, you cannot do like the parent folder. No, it was able to do that. Let me see. Okay, so here we should have out.rom. Yes. Okay, so you can write to the parent folder, but you shouldn't be able to use, for example, if example.tal where let's copy uxn example.tal here. So this wouldn't work, I believe. Let's see. Okay, yes. So in this case, this is invalid because there is a sandbox in the file system device, and it won't let you grab this file from the parent folder. So everything that is below the folder you are currently working on should work. In this case, it let us write outside of the sandbox, so I'm not sure if this is also like I'm not sure if this is also an error. So I'll just make sure why drift.rom allowed writing outside current dir. Okay. And if I find that any of these are actually errors that need to be fixed, I will make another stream making the pull request so that you can see also how you can contribute to any of these repositories. So with this, I say goodbye. Thank you very much for watching, and I hope to see you next time. Have a wonderful day.